So in this video I want to discuss the definite integral, and in particular I want to look at an approach to it which is called in mathematics the Riemann integral. So a definite integral like this one, the integral of a function f of x from a to b, is understood as in the following way. We can sketch the function that we're going to integrate, the integrand, and then we take any area between the curve of the function and the x-axis, and any area that is above the x-axis counts positively to the integral, and any area which is below the x-axis counts negatively to the integral. And here, for simplicity, I'm just drawing a function which is positive over the entire range of integration. So for the example as I've sketched it here, this definite integral is just this area. And in the Riemann integral, what we do is we approximate this area in two different ways. One way, which I've drawn in this graph, is to break it up into the sums of the areas of little rectangles, and as you can see from looking carefully at this graph, let's pick this particular rectangle here, its height is chosen such that it agrees with the minimum value of the function over the range of this little rectangle. So from here to here, the smallest value of the function is this, and this is chosen to be the height of the rectangle. So when I add these rectangles together, defined in this way, this is going to give me an underestimate for the correct answer. Moving now to the graph over here, the height of, let's again just look at this rectangle here, the one on the right, its height has been chosen such that it agrees with the maximum value of the function over the range of the rectangle. So it is going to give us, when we add this and this and this together, it will give us an overestimate. And what the Riemann integral does is to show that in the limit, as the number of rectangles approaches infinity, so there are more and more rectangles, which are all becoming smaller and smaller, but their sum hopefully gives us a better approximation to the true result for the integral. This underestimate and this overestimate agree, and therefore we can say with confidence that yes, this and this are giving us the correct answer. So that's the basic idea of the Riemann integral, and what I want to do in this video is to calculate a specific example of the sums of the areas of rectangles chosen in this way. So let's move on now to the next slide and do this for a simple example where it's easy to calculate the sum of the areas of the rectangles. So the example we're going to calculate is the integral from a to b of x with respect to x. So to understand what that is going to mean, let's sketch the integrand, and the integrand is just the line y is equal to x. So that's just going to be this straight line here. And what I'm going to do is I'm going to take this line here, I'm going to choose my integration limits, a and b, and I'm just going to write them here in this quadrant. You could experiment with changing that if you wished. And I'm going to break them up in this way. So this is my integral, this entire area here. The reason it's the area is because this is above the x-axis. If it was below the x-axis, if we look at a line down here, we would have minus the area for our integral. So this is what we're going to calculate, and we're going to break it up into the sum of various rectangles. And I'm going to choose rectangles which always lie below this line and just touch it. So I break it up this way, so first rectangle, then let's say a second rectangle, then let's say a third rectangle, and then a fourth one here. So our approximation with 4 rectangles to this definite integral would just be the area of each of these rectangles. Now, this is clearly not exactly the right answer. All of these areas here, shaded in yellow, are missed by our approximation. I'll just colour them in a bit. So the yellow areas that are drawn here are errors. But the idea is that as we make the number of rectangles larger, the number or the amount of the errors is going to become smaller. So this is our approximation, and I'm going to say now that we don't just have 4 rectangles, I've drawn it with 4, but I'm going to say that we assume that we have n rectangles. And what I want to do is to work out what the area of these rectangles is going to be. So let me just pause and make a little bit of room. So I think the first thing to notice is that if I break up my range of integration, which is b minus a, the width of the rectangle, remember we have n rectangles, and I'm going to call the width of my rectangle delta. That's going to be b minus a divided by n. So all I've said is that this distance here is b minus a. I'm breaking it up into n rectangles. I'm assuming here that the width of the rectangles is identical, so therefore each rectangle is going to have width b minus a divided by n. I now want to look at the heights of my rectangles, and this is where having a relatively simple function such as y equals x makes it quite easy to write this down. So the height of the first rectangle counting from the left, well, that's quite easy. It's just a. That was the value of our underestimate here. So the height of the first rectangle is a. We can now move on to the second rectangle. So the height of the second rectangle. So now we're looking at here, this rectangle here, we've gone from a to a plus delta, and the underestimate that we're using, the lowest value of our function here, is going to be the value of x at a plus delta. So this height is just a plus delta. So that a plus delta is the minimum value of our function in the range from a plus delta to a plus 2 delta, where the third rectangle commences. And in general, if we just carry on looking at this, the height of the ith rectangle, remember we have a grand total of n rectangles, is going to be a plus I minus 1 times delta. So that's our general expression for the height of the ith rectangle as we go along here. So this tells us what the total area is. The total area is the sum of the areas of all of these rectangles, and now we know what the width of the rectangles are. We have a general expression for the height of the rectangles, so we can put this together. So what we have is that the integral from a to b of x with respect to x is going to be the limit as n approaches infinity, so as the number of our rectangles approaches infinity, and then it is going to be the sum of I is 1 to n, so it's the sum over all n rectangles of their areas, and the area of each rectangle is going to be given by its width times its height. The width is a common factor, it's the same for everything, and for brevity we're just calling it delta. And then the height of the ith rectangle, as we've just written down here, is going to be a plus brackets I minus 1 close brackets times delta close brackets. So what we have to do to calculate this underestimate of the answer is to work out this sum, and then having worked out the sum, take the limit as n approaches infinity. So on the next slide we're going to look at this sum. So this is the sum which enters in our calculation of the definite integral of y is equal to x. So it's the sum over n terms. Each of them has a common factor of delta. Delta we've defined to be b minus a over n. And then the delta here is multiplied by a plus I minus 1 times delta. So we're summing over I, and some of the terms don't depend upon I at all, and some of them do. So let me rewrite our sum in a way that separates out the I dependence. So we have delta times a minus delta plus delta squared times I. So what I've done here is I've said here I've got a minus delta multiplied by delta, and then I've got this I times delta, and there's a delta out here, so that's delta squared times I. So this is really, we can think of this as the sum from I is 1 to n of delta times a minus delta plus a separate sum, and that's the sum I is 1 to n, and then in each of those terms there's an I, and they're all multiplied by the common factor of delta squared, so I can actually take the delta squared outside the sum. Since it multiplies every single term, we can just think of it as multiplying the total answer. So here we have this term, and we just add it without any change because none of this depends upon I. We add it together 1 time, 2 times, 3 times, up to n times. So this is just going to be n times delta times a minus delta. And the second term is delta squared multiplied by, and this is a very standard sum, and its result is n times n plus 1 all over 2. And in case you don't know this result, at the very end of the video I will give you a very, very simple proof of it, but at the moment I don't want to do that because I don't want to break up the flow of the calculation. So I'd just like you to take this result on trust, should you not know it off by heart. So we now have our result for the sum, and what we're interested in is the limit as n approaches infinity, so it's useful to rewrite it in expressing the delta in terms of n. So what we have is our first term, we have n times delta, and n times delta, if I multiply delta here by n, the n will cancel, I'll just be left with a factor of b minus a. So I have b minus a. And this is multiplied by a minus delta, and delta is b minus a all over n. I'll put brackets around that. The next term is delta squared, that's b minus a all squared over n squared, multiplied by, on the bottom there's a half from here, and on the top we have n times n plus 1, and I'm going to expand that. I'm going to write this as n squared plus n. So this is our result for the sum expressed in terms of n and a and b, which are just our integration limits. So what I want to do on the next slide is look at the limit of this sum. So just to recall what we're doing, we're interested in the definite integral from a to b of x with respect to x, and we've said that this is the limit as n approaches infinity of the sum over Sn, where Sn is a sum, and we've calculated this to be Sn is b minus a, this is the last thing we wrote on the previous slide, times a minus b minus a all over n, plus b minus a all squared over n squared, times n squared plus n all over 2. So therefore, that's our sum, but we don't want the sum for any particular value of n, we want it as n approaches infinity. So the limit as n approaches infinity of Sn is going to be, well, let's just look at these terms first. Here we have b minus a times a. So that's b minus a multiplied by a. That doesn't depend upon n and is in no way changed. We then have minus b minus a times b minus a, so that's b minus a squared over n, but as n approaches infinity, b minus a squared all over n is going to approach 0. The next term that we have is b minus a all squared over 2. I've just taken this, and that's going to be multiplied by n squared plus n over n squared. So it's going to be the limit as n approaches infinity of n squared over n squared plus n over n squared, all of that in brackets, and that is multiplying this. Now n squared over n squared is just 1, and 1 as n approaches infinity stays 1. Here we have n over n squared, that's 1 over n, and the limit of that as n approaches infinity is going to be 1 over something approaching infinity, it's going to approach 0. So we're going to get 1 plus 0, so this whole term is going to approach 1. So therefore we see that our integral from a to b of x with respect to x is going to be b minus a times a plus b minus a all squared over 2. And the last term here is just multiplied by 1, so that's all we have. So this is going to give us the b times a minus a squared, just expanding this out, plus, and then we have a half b squared. The cross terms are going to be minus 2ab over 2, so the 2's will cancel, so I get minus ab, and then I get the minus a squared, so that will give me plus a squared over 2. And we see here that the ab and the minus ab will cancel, so they go. We have therefore that our integral is going to be equal to b squared over 2, that's this term here, minus a squared plus a squared over 2, so that's going to be overall minus a squared over 2. And this is our answer for the integral. So I'll just make some room to write it nicely. So we conclude that the integral from a to b of x with respect to x is b squared over 2 minus a squared over 2. Now, one thing that you might worry about is that what we've calculated here has clearly been an underestimate. We had all of those possible errors, and those possible errors were all such that we were perhaps underestimating the answer. So what I'd like to do on the next slide is just to talk about how we could actually see that that's not something to worry about. So what I want to do on this slide is to just discuss another way of approaching this problem. So I've drawn the same graph as before. We're interested in the same integral, but what I want to do is I want to break it up into a different set of rectangles. So what I'm going to do is I'm actually going to start at this side here. So I'm going to draw a rectangle here whose height is this, and I'll then draw a second rectangle whose height is this. In this case I'll just break it up into 3 rectangles. And what we say now is that the integral is going to be approximately given by the height of all of these rectangles put together. And of course there is an error in this, and the error here is again these yellow triangles. But what we have now is we have, by adding the areas of these rectangles together, we have an overestimate. This is, for any finite number of rectangles, always going to be larger than the integral correct value. But again, what we can do is we can show that as n approaches infinity, we get exactly the same answer. So I'm not going to do that in this video, but I'll leave that perhaps as an exercise for you to think about or to check. Show that as n approaches infinity, this overestimate converges to b squared minus a squared, all divided by 2 as well. And this is an example of something which is known as the squeeze rule. So let me just pause and make a little bit of room. So what I want to say now is the following. We've calculated the integral over the previous few slides, the integral from a to b of x with respect to x. And what we calculated was, for any finite value of n, going to be an underestimate. There were those yellow triangles that we had neglected. So our answer that we got was always going to be an underestimate, and as n approaches infinity we hope we're getting the same answer. So we get b squared over 2 minus a squared over 2. And if you take this exercise here, what you will see is that as n approaches into infinity, the overestimate gives exactly the same rule. So we get, or the same answer, we get b squared over 2 minus a squared over 2, and the integral is greater than or equal to this answer. Now, if we have something which is greater than or equal to something, and it's also less than or equal to the same thing, then there is only one possible logical outcome, and that is that it must be equal to this. And that is what's called the squeeze rule in mathematics. If my integral is less than or equal to this, and it's also greater than or equal to the same thing, it must be equal to that answer. So this is called the squeeze rule, and I'll just make myself some room. So therefore, from the squeeze rule, the answer here in the middle is squeezed into there, and the only logical outcome is that it's equal to this quantity. We see that the integral from a to b of x with respect to x must be equal to b squared over 2 minus a squared over 2. So with that, I've concluded this discussion of this simple definite integral, and I've tried to give you an idea of how one can calculate such sums, and in that way one can work out what the areas are, and how through having consistently a series of underestimates and also, as I've drawn here, a series of overestimates, and showing that you get the same limit from both answers, that squeezes the right answer into definitely being that outcome. So what I want to do now is to move on to a final slide and just show, as promised, the result for the sum over the first n integers. So I'll just move on to another slide to do that. So what I want to do is just to show why it is the case that the sum over I from 1 to n, so the sum of the first n integers, is n times n plus 1 over 2. And to do that, what I'm going to do is I'm just going to write out our sum. So it is 1 plus 2 plus 3 plus ... plus n. And then I'm going to take exactly the same sum. It's got the same number of terms, but I'm going to count from the top down. So I'm not going to say 1 plus 2 plus 3 plus 4 plus blah blah blah. I'm going to say we're going to have n plus n minus 1 plus n minus 2 plus blah blah blah, and the very final term is of course going to be 1. So having done that, I now say I want to add them. So therefore 2 times Sn is going to be, and I add those two together and I get 1 plus n, which I'll write as n plus 1. When I add these two terms together, I have n minus 1 plus 2, and that is again plus n minus 1. And you can see very easily that all of these pairs, when I add them together, are all going to give me n plus 1. And if you think about it, what's happening here is here I have an n, here a 1. As I go this way one step to the side, I drop this down by 1, but I increase that by 1, so the sum stays constant. So that's why we have these n plus 1s. How many of these terms are there? Well, there are n of them. There are n pairs. So therefore, we have twice the sum is n times n plus 1. n plus 1 was the answer for each of the pairs, and there are n such pairs. So that tells us that the sum Sn, which was again the sum I is 1 to n over I, 1 plus 2 plus 3 up to n, is given by n times n plus 1 divided by 2. And with that, I'll stop this video.